Okay, if Scott's ready, we're going to go ahead and get started. Thank you for joining our webinar, The Samurai System for Service Call Excellence. Scott Brown is going to be your facilitator today, and he is with the Master Samurai Tech. Scott, if you're ready, go ahead and take it away.
Okay, mic should be on. We have a hot mic. All right. Sorry about the delayed start, everyone. Thank you, Sarah, for your patience. Thank you, everyone else, for your patience as well. A little bit of a late start here, but thank you all for coming out. And today we're going to be talking about the Samurai System for Service Call Excellence. So before we get started, as Sarah mentioned, my name is Scott Brown. I'm also known online as Samurai Appliance Repairman. And together with Team Samurai, I run the Master Samurai Tech Academy and Appliantology.org. I encourage you to take notes during this little presentation today. We're going to be covering a lot of material, and so notes will be very helpful for you in referring back to it. We're going to get into some preparatory information as well as technical information. What we're going to be talking about today is a system for running service calls. And a system is just a coherent, well thought out set of standard operating procedures for doing things efficiently and facilitating successful transactions. And in the world of appliance repair, when we talk about successful transactions, that means we're talking about a successful repair. So we're going to be talking about ways of preparing for and conducting service calls that you've already carefully thought out ahead of time. Keep in mind, if you deviate from your system, whatever it is, and I'm going to present to you a system that I use, hope it will be helpful for you. If you deviate from that system, you only do so deliberately and for special exceptions, which should be 1% or less of your service calls. Because if you deviate from your system in the midst of a firefight, in the middle of a service call, making spot decisions, just keep in mind you may result in messy situations. So there are always exceptions in our service calls, but that's not what we're talking about today. We're talking about a system. And the objective of any system, and particularly the one I'm going to be sharing with you today, will be maximizing your first call complete, or actually in this day and age, it's more realistic to talk about second call completes with all the different boards out there. Reduce time you spend on the calls, figuring it out. Reduce time spent on the phone with TechLine, because nothing says incompetence like on the phone with TechLine. Eliminating unnecessary disassembly, that's a big one. A lot of techs waste a lot of time doing unnecessary disassembly when most of your troubleshooting can be done from a convenient central location, such as a mechanical timer or a control board. You want to look like a real pro to the customer because that's going to inspire confidence. It's going to discourage things like what I call the technician witch hunt. That's where you've completed a repair, but now, oh, it didn't make that noise before. And oh, that didn't do that before, when in fact it did, but you've come under the microscope because you've not inspired confidence. This is going to end up increasing both their satisfaction with your work and your income. So again, as I mentioned before, 99% of your service calls should be handled according to a system. So I'm going to offer you one today that I've developed over the years. I've been doing appliance repair for over 20 years and running online appliance repair communities for over 20 years. I'm going to be sharing with you a system that I use in preparing for service calls that hopefully will be helpful for you. You can adapt this as for your own needs, however you like. But what I'd like you to come away with today is the importance of doing service calls according to some kind of well thought out system, whether you use mine as presented or adapt it to your needs. In this system here, and there's really not that much to it. Validate the model number, you can read them right up here. But all of these steps in blue, and we're going to be talking about each one of these, are done before you even walk into the door. So the service call starts before the service call. You're going to be doing your homework, getting the model number, technical literature, formulating a problem statement, wargaming that statement on the schematic, and you're going to have all of your tech literature on your tablet device, already bookmarked and for quick access, ready access when you're on the call. The red step down here, where you may revise your problem statement based on your actual findings, that's done obviously at the call. A lot of times we get information from a customer that is incomplete, or there are things going on that they weren't aware of, they didn't think to tell you. So you have to just be prepared to revise your strategy, your plan of attack, while you're at the call. So let's go through each one of these. The first thing you want to do is validate that model number as given to you by the customer. You can't research the technical literature, which is another crucial step in the system, without a valid model number. And when we're talking about technical literature, we're talking about things like your tech sheet, your fast track, your mini manual. A valid number, you're looking for, a valid model number is going to let you get two key things that you're looking for: the schematics and the specifications. In the case of a machine that has a mechanical timer, you need that timing chart. When you're dealing, and in the case of computer-controlled appliances, you need that key dance to be able to talk to the board so that you can retrieve error codes. All of this should be planned out, and you should at least get eyeballs on this beforehand. And you're going to need the service manual. Mostly what I use service manuals for is the disassembly procedures. So common model number mistakes that I see, for example, at Appliantology when techs are looking for either help or for technical literature, is they'll give an incomplete model number, they'll give a serial number instead of a model number. Customers will do this too, of course, which you expect from customers, right? But we as technicians, this is our bread and butter. We should know that everything starts with a model number. So we should be able to get a valid model number and validate it and make sure that it's correct. You'll often get an incomplete model number. For example, in Kenmore appliances, they'll leave off that prefix. O's are often reported as zeros or vice versa. I's for ones, S's for fives, 6 for G's, and there's probably many other examples. And here's an example of a technician, this is over at Appliantology, looking for some technical literature on a Frigidaire dryer. And can you spot the problem with the model number here? And he says he's validated it over at Repair Clinic. Now, sometimes you got to watch out when you're validating, they'll autocorrect because the online parts houses will also autocorrect for common mistakes. In this case, what he's done is, you notice this slight difference in characters here. These are all zeros, and he's got a capital O over here on the end. Well, in this case, that's an invalid model number. That's supposed to be a 0. That's one example. Here's another example where a tech is at Appliantology is looking for technical literature, and on a GE Monogram vent hood, does this look like a model number for any Monogram vent hood that you've seen? I mean, what he's done there is given a part number instead of model number. So that's just another example. And had he validated it, like he said he did, that would have come up with a part instead of with a model. So just things, we have to be aware of that as technicians. We're all about details. It's right in the name, technician. We're all about details, and we need to pay attention to these kinds of things. Better yet, pro tip is have the customer text or email a photo of the model number tag to you. The reason this is important, not only does it ensure that you get the correct model number, but a lot of times the model number will have other information on it that you need in order to find the technical literature. Examples are, you need the type number in ASCO appliances, or you need the BOM number at Samsung appliances. Let's look at that. So here's an ASCO model number. A lot of times if your customer calls in or emails in, whatever, they're going to give you just this model number here because that's what you're asking for. But really, in the case of ASCO, what you need is the type number in order to be able to find technical literature. So, and again, all this information is on the model number tag. Unless you know to ask the customer for the type number, the customer isn't going to necessarily report the type number to you. They're just going to give you the model number. In the case of Samsung appliances, a lot of times they'll have the model number right here. They'll call it out as a model number. But what you need to be able to find technical literature for Samsung appliances is what's called the BOM number. And that's this slash and these 3 characters at the end. That tells you the country, the destination country that it's headed towards. And if you're going to look up technical literature for that Samsung appliance, you need this because the technical literature is going to be slightly different for an appliance built for the US versus one built for Canada, etc. All right, so then you're going to validate that model number you're going to run that model number through one of the easiest way to do it is use one of the online parts houses. Use your favorite one. I've just given some examples here. Repair Clinic, Appliance Parts Pros, Sears Parts Direct, in the case of Kenmore Appliances, a good resource to use. and validate it. Make sure it comes up right. Contact the customer and get the correct model number if you need to. And again, the whole point with doing this is you cannot get the technical literature you need without the valid model number. And without the technical literature, you can't adequately prepare for that job. You can't war game it against the problem statement. So you need the model number. Sometimes you can figure out what's wrong with the model number and fix it yourself. Otherwise, you may need to contact them and call them back, or your CSR calls them back, and you get the corrected model number. Once you've validated that model number, you want to download the technical literature and review it. And again, as I mentioned, you're looking for two main things, the schematics and the specifications. So what I find is a lot of techs don't have a good understanding of specifications. We're going to spend a good bit of time today talking about specifications because they're very important for us to be able to do our jobs. We'll often use, as techs, terms like good or bad. Well, that's really kind of a qualitative assessment. There are definitions for that. The definition of a bad component is that it no longer conforms to the manufacturer's specifications, right? We use specifications to determine whether an electrical measurement that we make with our meter is, quote, bad or, quote, good. In other words, what we're really saying when we use bad or good is the component in spec or is it out of spec? In the world of specs, we're dealing with three different types. We have explicit specifications, such as what are printed right on the tech sheet or on the spec block on the tech sheet. For example, thermistors, and we'll see some examples of that. There can also be implicit specs. They're implied. They're either derived from explicit specs or from what we should already know as technicians about the way things work. For example, how a split-phase motor operates, how a BLDC motor operates. Ohm's law, we should be able to shift Ohm's law around in our head if they give us just two specs and we want to derive, if they give us, for example, watts and they give us volts and the power supply for that load, then we want to be able to derive amps so that we can do an amp reading. You should understand how circuits work. You should understand about data lines, how they function, that you're always working between some voltage between 1 and 4 volts. In the digital logic world, you've got a series of 5-volt pulses. Your meter will average those out. Power supplies and how they work and how they're subject to failure, particularly in the DC world. This whole idea of loading down, we'll talk a bit about that as well. And finally, something that trips a lot of techs up is this whole idea of omitted specifications. And you see a lot of manufacturers will do this. They'll omit specifications, for example, on how two boards are talking to each other. They won't give you anything about how that harness is connecting to each other. Either what's DC voltage, what's communications, what's DC ground. They won't call those out. We'll see an egregious example of that here in just a few minutes. So let's look at some examples of these different types of specifications: explicit, implicit, and omitted. And we're also going to talk about how we handle the special case of omitted specifications. Here's an example of explicit specifications. This is from a Samsung refrigerator on their Fast Track. You will find this table on every single Samsung refrigerator Fast Track. These are very granular. Notice look how detailed the temperatures are. They're giving you ohms, but better than ohms, they're giving you volts. And you always prefer to work in volts than in ohms. Ohms are kind of a noisy measurement, but volts are usually a lot more accurate. And you know what I mean by noisy measurement? So you take your voltmeter or your multimeter, you put it on ohms, you short the leads together, and there could be some residual amount of resistance that's showing up on your meter. That's noise. And that's could be oxides on your leads or whatever. But if you're dealing with volts, you don't have to worry about that. Anyway, this is an example of explicit specifications. Here's an example from a Whirlpool tech sheet, another example of explicit specifications. And again, we're looking at the thermistor here. They don't give you the granular resolution that Samsung does. They just give you 3 data points, and they just give it to you in ohms. Not ideal, but we work with the specs that we're given. And they give you a little tolerance on that too. This plus minus, so this is the spec, 2,700 ohms, and this plus minus is the tolerance. So you're allowed a variance of plus 5% or minus 5% on that spec. All right, so let's look at an example of implicit specifications. Again, this is from that same Whirlpool text sheet showing specifications. And here let's look first at the defrost circuit, what they're calling out as the freezer evaporator heater. So they give resistance, 30.4 ohms, plus or minus 5% is your tolerance on that. But good techs know not to rely on ohms readings to declare an AC component, quote, good. And the reason is that if the ohms read open or infinite resistance or way out of spec, then yeah, you've found a problem. But if the ohms read good, that doesn't necessarily mean that the component is good. You can't declare that at that point. And the reason for that is that the component may read good under ohms, but start what we call failing under load when electrons start blasting through it. Those electrons traveling through the component or the wires or the connectors to that load can cause it to fail under load because those electrons create heat. Heat creates expansion in metal, and then anything that tends to separate will do so. So the dead, surefire way is to test all of your AC loads under load. And to do that, you would want to measure amps. All right, so we've talked about the tolerance a little bit. What I wanted to talk about was this idea of the preferred way to test this defrost circuit or any AC circuit. And as I mentioned, you want to do that under load, and that means you want to energize the circuit and measure amps. But they don't give us amps in this case, do they? I see resistance, I see watts, I see volts, but do they give us amps? Well, this is an example of implicit specifications, because in fact they are giving you amps. Because in this case, if you know volts and you know watts, you know amps, because you would just use Ohm's law to figure out what the expected amp reading would be. So you would force defrost on the unit by whatever the key dance is on that particular control board, and then clamp your amp clamp around the wire going to the load of interest and see if it's in the expected range. And how would we do that? Well, if we know, being techs, and we know this stuff, that P is equal to I times E, and that little star there is a multiplication sign. So if I'm trying to solve for amps, the expected reading, then I know that I is equal to P over E. And if I run the numbers on that, well, let's just plug in our numbers here. 435 watts, right? They give me that, 435 watts. And then they're using 115 volts. That's kind of an old school designation. Nominal voltage in North America is actually 120 VAC. So that's what I'm going to use, 120 VAC, right? So that gives me 3.6 amps. It's supposed to be a 3. So that's my expected reading if I'm testing that load under load. If I'm testing that, in fact, I'm testing that entire circuit under load. But now if I apply the tolerance, I've got plus or minus 5%, and I just apply that to what we just calculated there, 3.6 amps. I'm allowed a variance, so my variance on that will be anywhere from 3.4 to 3.8 amps. So if I put my amp clamp around the wire going to my load of interest, and I measure anywhere from 3.4 to 3.8 amps, I'm in spec. And that's an example, again, of implicit specs. They've given me everything I need to derive that without ambiguity. I don't have to guess. They've given me the numbers, and I've used Ohm's law to derive what my expected amp reading should be. All right. Let's take a look at the evaporator fan up here. Now, this is really odd. And this is kind of typical. Whirlpool will do this a lot of times. They just kind of get lazy on their data tables. And notice up here, they're giving me volts, and they're telling me clockwise. Huh? What does that mean? Clockwise voltage? So, and then they give me a resistance right here of 5 plus or minus 15% watts. Wait a minute. I thought resistance was measured in ohms. does this mean that power is equal to resistance in this particular motor? Is it some strange motor? So without even looking at the schematic and just looking at these specifications as given, what do we know about this motor? What kind of motor do we know that we're dealing with? And by the way, you guys can put things into the chat box, and I hopefully should be able to read them. Anyway, what kind of motor do we know that we're dealing with given these types of specifications that are badly named and badly labeled? They're giving me watts. Notice also the power supply here, 12.7 volts DC. Am I dealing with a typical shaded pole motor? No, a shaded pole motor runs off 120 volts. I know that as a technician. So right away, I know they're giving me watts, they're giving me a DC voltage power supply. I know I'm dealing then with a BLDC motor, a brushless DC motor. Put that up here. A term everyone should be familiar with, brushless DC motor. I know this without even looking at the schematic, just based on the specs that they're giving me. So if we're troubleshooting from the board, as we should be, what kind of electrical measurement can we make in this case to tell if the evaporator fan is running or not? Do we have to go around, we're already in back behind the unit, working at the main control board. Do I have to get up and go around to the front and open the door and push in, find the light switch and push in? Or can I do it all conveniently from back behind at the control board? I've got my meter, I've got the schematic, I've got the specs. Watts would be optimal if they give me watts, but how many of you carry a clamp-on watt meter? Actually, techs used to carry a watt meter, but those are old school days. Because techs used to know that loads are all about watts. So I don't carry a clamp-on watt meter. I don't even know if there is such a thing. But every one of you should have a amp clamp in your tool bag. So knowing that, I should be able to, with the specifications they've given me, I should be able to derive what my expected amp reading is. How would I do that? Well, I'd still use our friend, P is equal to I times E. And let me just erase some of this. And now instead I'm going to plug in the specs that they've given me for power and voltage, which again, they've given me over here. Get rid of some of that. They've given me 5 watts at 12.7 volts DC. Okay, good. I can plug that in just like I did before. I won't go through that again. But if I plug all that in, I get an expected amp reading of 0.3. That's supposed to be a 3. 0.39 amps. Or 390 milliamps. And if I apply the tolerance that they've given me, and my tolerance is plus or minus 15%, and so then I know that if I read anywhere from 330 milliamps to 450 milliamps, that I'm in spec within the tolerance that they've given me. So then I'm going to use my, now, let me ask you a question here. Are these AC or DC amps? It's a BLDC motor, and in the case of an evaporator fan motor, that inverter is built into the casing of the motor. That's there in the refrigerator above the evaporator. So in this case, the board is just supplying DC voltage to the inverter, and then the inverter is doing its job of making the motor itself run. So am I measuring DC or AC amps? And you know from the spec that it's DC voltage, so I'm measuring DC amps. Those amps, those electrons are always traveling in one direction in that circuit. It's not alternating back and forth like in AC. How am I going to measure DC amps? Well, it turns out that you can. And The way you do that, you get a multimeter that's got an AC and DC amp clamp. They actually make such a thing. If you go over to Amazon and you search DC amp clamp, just search that term at Amazon, you'll find this meter. This is the exact one I have, and it runs about 50 bucks. It's not a common measurement that you'll need to do, but when it's a small little meter, you can easily make space for it in your bag. And when you need to do it, though, it's convenient to do. It's a very powerful diagnostic tool. All right. So let's talk then about omitted specs. This is something that trips a lot of guys up. And before we talk about omitted specs, we have to talk about what analytical troubleshooting is. Analytical troubleshooting, very simply, is just you're generating a number on your meter, and then you're comparing that number that's shown on your meter display with the number in the specifications. And then you, as the technician, are drawing the correct conclusion. In analytical troubleshooting, your troubleshooting stops where the specifications stop. Because you need specifications to tell you what your electrical measurements mean, whether you're dealing with volts, amps, ohms, frequency, whatever. In other words, is it, quote, good or, quote, bad? And so without a spec to tell you that, you can't do analytical troubleshooting. There is another type of troubleshooting that you can do, but it doesn't involve generating a number, and we're going to talk about that other type of troubleshooting. But in analytical troubleshooting, without the spec, either explicit or implicit, you can't compare something to nothing. So they've shorted you on information. And you need to recognize this as the tech. You need to recognize when the specs are omitted, because that's just as important as recognizing and using the specs that are given. In these cases, you may be able to deploy non-analytical troubleshooting techniques in order to prove the problem. Now, I say non-analytical troubleshooting techniques contrasted with analytical troubleshooting, which again is generating a number on your meter and comparing with the number in the specs. A non-analytical troubleshooting technique is you're not generating a number, but you're employing some type of technique like isolation, half splitting, jumping the switch, cheating the load, and we'll talk a little bit more about some of those. A technique, this word here, technique, is very important because we're going to contrast this with things that are not techniques that are often confused as techniques, that they're just simply methods. But a technique is something that you do with your hands based on knowledge in your head. So you're applying strategic procedures or methods in order to affect a desired result, and that is a successful repair in order to prove the problem. Troubleshooting, whether it's analytical or non-analytical, proves a problem so that when you replace the part or parts, you know it's going to be a 100% guaranteed fix. So let's talk about things that are not troubleshooting techniques. None of these are techniques. You're not actually deploying a strategy in your head and implementing that with your hands. Things that are not techniques, but they're often confused as techniques. And these are things like anecdotes. Anecdotes are like little stories. Well, I had that problem one time and someone told me to replace a particular board and that got it. Another one is intuition. My gut tells me that it's a bad particular board. Or beliefs. I hear this kind of language a lot. Well, I really believe that it's this, but that's not a technique. Okay, these are all just different types of methods, to put it kindly. Heuristics is another one that I see a lot. Heuristics is a fancy word for rules of thumb. For example, TechLine calls and they say most of the time, that's typically how a heuristic goes, the problem is a particular board. And if that doesn't fix it, then replace the other one. And that kind of leads into the trial and error. Well, I replaced a particular board and that didn't fix it, so then I replaced the other board and then that fixed it. That's trial and error. Now, none of these are troubleshooting techniques, either analytical or non-analytical, but they're often confused as such. They're just guesses. Whether educated or not, they're still just guesses. Now, you may get lucky and you may actually fix the problem with one of these methods, but again, we're talking about systems here. We're talking about how you normally roll, SOPs for how you handle these things. You may get lucky and actually fix the problem with one of these methods, but that's not troubleshooting. It's called something else. This is called lotto. Okay. Lotto methods are not techniques because they don't prove anything. You're replacing a part and hoping to get lucky. Now, everything's fair game on a service call. The mission is to get it fixed, but you as the tech should recognize when analytical or non-analytical troubleshooting techniques stop and when you may choose, hopefully very infrequently, to deploy a lotto method. You may choose to play lotto, but this should come after all your troubleshooting. Personally, I don't. I don't play lotto. I don't do any of that. If you do play lotto, you should do so deliberately, consciously, and rarely, painfully aware that you're making a guess and you're relying on luck. So let me ask you, is relying on luck a good strategy or system for ensuring long-term business success and profitability? I would submit to you that it is not. So how do we handle then calls where needed specs are omitted? So I have separate webinar recordings over to Pliantology on non-analytical troubleshooting techniques, loading down, jumping the switch, cheating the load, whatever, and those are available over to Pliantology for members to watch. But in handling these kind of situations where specs are omitted, you need to recognize when the manufacturer is omitting specifications from you, and that therefore they're limiting how much you can troubleshoot. So what I do is I narrow down to the fewest number of parts that I can using either analytical or non-analytical troubleshooting techniques. If I've run out of specs, then I'll deploy non-analytical troubleshooting techniques, real techniques, to try to narrow down the problem. And some of these techniques, as I've mentioned, are things like isolation. So isolation would be very useful in a case where you have, typically it's a case where you've got a DC load and a DC power supply on a board, and the resistance of that load has gone so low that the DC power supply on the board is trying to force too many electrons through it, and it's going beyond its rated wattage. Every DC power supply has a rated wattage, 3 watts, 5 watts, whatever. And if the load goes so low resistance that that voltage is trying to push more electrons through than the DC power supply on the board can handle, then your voltage is going to drop off. That's called loading down. Isolation is a technique to deploy in that case. Half splitting. So for example, you're dealing with a warm refrigerator, both compartments warm. So right away you want to half split. Is the problem in the sealed system, or is it everything else, something else, everything else in that box that's causing the problem? That's half splitting. If it's a sealed system problem, there are ways of figuring that out. We'll talk about one easily. There are easy ways of figuring it out without having to put on gauges or anything like that. Then you can half split the problem between the sealed system and everything else in that box. Jumping the switch. So you've got a switch. I like to work on live circuits. It's the most reliable way to troubleshoot. It's the most expeditious way. So I can jump that switch and see then, does my load start functioning? Use a jumper wire of the appropriate gauge to jump the switch. If a load isn't working, particularly like AC loads, you'll see this, then you can cheat the load. Use a cheater cord and directly power the load and see if then the load will start running. If it does, then you know there's a problem with the supply circuit for that load. So the point is that you want to already have an SOP game plan for handling these types of situations as part of your system. And the idea is you're trying to get to a proven solution. That's a solution proven by troubleshooting, either analytical or non-analytical. And again, lotto methods do not prove anything. You're replacing a part and hoping to get lucky. So let's look at an example. Another example of a non-analytical troubleshooting technique, but it is a real technique, and it's based on your knowledge and understanding of various types of systems and circuits and technology that we work with as techs. Example here is you got a Whirlpool Duet washer. Won't run, won't go into service mode. So right away, because you understand how variable frequency drive systems work, such as what we teach in fundamentals, you understand how they work. You understand Whirlpool has a MCU. In this case, Whirlpool likes to use dumbed down names for things. That's really just an inverter. And you have a CCU, as they like to call it, which is just the computer. So you would isolate one from the other, because this may be a loading down situation where the inverter is loading down the computer, the DC power supply on the computer. So you isolate it by simply disconnecting the wire harness. Super simple, right? But you had the wherewithal in your head to know to do that because you understood loading down. You are deploying a non-analytical troubleshooting technique in order to prove the problem. So you do this, you disconnect that MI3 connector right from the CCU, and then you can enter service mode. You've proven that the MCU is loading down the CCU, that the inverter was loading down the computer. Now some guys will say, oh, okay, now you tear it apart, get down to the MCU, get down way down in the belly of the beast, take the whole thing apart, and then, oh, you might find a swollen cap. Look, I'm not going to play that, and you guys may choose to, but I don't do that. If it's a bad board, I got other jobs stacked up waiting for me. And so I'm not going to sit there and tear down the whole appliance in order to replace a little capacitor on a board. No, if I prove, rather I can reach the CCU by simply removing the top panel of the machine, and I disconnect that MI3 connector, and suddenly I can enter service mode, I have proven that the MCU is a problem. I don't need to get eyeballs on it. I've already proven it. So when I come back on the second trip, I'm going to have that MCU with me. I'm going to disassemble once, and that's to install a part. My troubleshooting is done with minimal disassembly. Okay? And so once I tear it apart, I get down to the MCU. They're getting a new MCU. I'm putting that in, I'll test my work, and then I'll get paid, and I go on to the next job. That's the system of how it rolls. So all of that required that you have a functional understanding of the concept of loading down, how DC power supplies work, and how variable frequency drive systems work. So it was truly a troubleshooting technique. Excuse me. Let's look at another example here of omitted specs. This is a KitchenAid range, and you'll see this a lot of times. And this is a problem where you're troubleshooting a problem where the warming drawer, and here's the warming drawer right here, it randomly turns itself on. Now, just looking at it, this is most of the schematics, not all of it, but it's most of it. It's all the relevant parts are shown here anyway that could possibly be involved with this warming drawer getting warm for no reason. Nobody touched the panel, nobody did anything. They just come out and the warming drawer is going. If you look at the schematic, such as it is, you see that there's three possible components involved in this. You got a keypad. In this case, it's a capacitive touch key panel. Everybody know what a capacitive touch key panel is? Touch panel, whatever you want to call it. There's no moving parts in a capacitive touch panel. It's just the glass, solid glass panel. You touch your finger on the glass, and the input is accepted. There's no membrane. There's no moving parts. But that's one of the potential items involved here. And I want you to look at the other one is the user interface board. There's a whole board that has a display built on it. So they're giving me nothing here of the harness of how the keypad's connecting to the user interface. And I got a bunch of connections there. The third component that's involved in this is what Whirlpool is calling the appliance manager. And the appliance manager talks to the user interface board through this 4-wire connector. And they're not telling me anything about this. They're not giving me any of the pinouts on this anywhere on the schematic or in the spec sheet. So how do I know which one of these is causing the problem, right? It's got to be one of these causing the problem. The warming drawer isn't going to start sucking electrons out of the air and warming itself up. Somehow this relay is closing. And that could be due to some malfunction on the appliance manager causing the relay to close, some malfunction on the user interface telling the appliance manager to close this K9 relay. Or how likely is it, again, this is a capacitive touch panel, how likely is it that the keypad is a problem based on your experience? How often do you see capacitive touch panels fail, barring them being physically fractured, or they have a bunch of roaches behind them, stuffed into them or mouse droppings or something like that. Something is physically impairing that touch panel. Assuming that's not the case here, I've taken it apart, looked at that. I don't see capacitive touch panels fail hardly at all for some non-physical reason. There's just nothing going on there. Membrane touch panels, yes, they fail all the time. You get a membrane that wears through and you get a stuck keypad error or a stuck keypad that's causing a problem. So right away, I know, given that this is a capacitive touch panel, I can rule that out. Which components then, what would I do? How would I handle this? That leaves me with a user interface and an appliance manager. How do I know which one is the problem? And here's the answer. The answer is I don't. And so what am I going to do? I'm going to quote the job for replacing both the user interface and the appliance manager. And when I come back, and I'm really going to install both the user interface and the appliance manager, and I know it's going to be 100% guaranteed fix on my second call, because I don't stock this stuff. You shouldn't stock a lot of control boards anyway, because they upgrade the software, upgrade the hardware, whatever. They can go bad from humidity, sitting on your shelf, bouncing around your truck, whatever. Just order them as you need them. That's why I say it's more realistic to talk about second call completes these days when we're dealing with the world of computer controlled appliances. So yeah, I would actually replace both of those boards. I'm not going to quote both boards and come back and just try the game of putting in one and then, oh, that fixed it. And then that's not a good system. A good system is quote both boards. If they accept the job, they get both boards. I'm not going to just give them one and then still charge them as though I put in both. That's called stealing. And if the customer doesn't accept the job based on this, based on the cost of replacing both the user interface and appliance manager, fine. I got other jobs. I'll go on to the next one. It's not my fault. Why should I be penalized for Whirlpool shorting me on specifications that I need to pinpoint the problem down further? Right? So their problem in this case is with Whirlpool, not with me. I've done my job as a tech. I've troubleshot it down to the fewest number of parts that I can, given the limited specs that Whirlpool has provided me. All right, so these are just examples of how you handle situations with omitted specifications. All right, so jumping back then to our system, once we've validated that model number, we're going to download the technical literature to your tablet device. And search the files section at Appliantology. If you don't find it, you can post a request, or go to the USA Files Library, or go to MSA Files Library, whatever, wherever you go to get your technical literature. Get it before the job. That's the point. And put it on your tablet. And on the tablets, and we're going to look at this in just a second, you can use a couple different apps, several different apps actually. I've only listed a few here. Goodreader, PDF Expert, Evernote, Dropbox, whatever you like, whatever you're comfortable with. Doesn't matter. The point is to have it on your tablet before the job and actually review it. So just to show you what it looks like, here's Goodreader. This is actually a screenshot from my iPad. And so I can have things loaded in files, I can search, and I can bookmark separate files for relevant information that I know I'm going to be using on the job. Okay, here's the schematic, here's the specs, here's disassembly information in the case of a service manual. PDF Expert is similar, and I'm kind of experimenting with this one. This is, again, another screenshot from my iPad. But the idea is it's on your iPad, you've already reviewed it, it's there with you on the job, already loaded on your iPad and bookmarked, ready to go, so you can quickly find your way around. So let's review the system here, the system that I do, that I'm offering to you today. Again, all of these blue steps are done before you walk in the house. And you see that these aren't numbered. Steps 2, 3, and 4 kind of all inform each other and interact with each other. So let's talk about formulating a problem statement. When you get an appliance service call request, you're going to get all kinds of gobbledygook from customers. LG range not heating accurately, understating. We think this is an actual service call request, understating. I guess they meant to say undershooting. This is an email request. We think it's the convection fan or maybe the sensor, but don't think the fan is spinning. I don't care about any of that stuff. All I want to know is what is my problem statement is LG range not heating accurately. I have a heating problem in the oven. All customer diagnostics are immediately discarded. I have to get my own data. I don't care what they think. I want to know what they observe. I'm not interested in their opinions. It sounds kind of harsh, but this is kind of how you have to think as a technician. You have to stay disciplined. You can't let customers direct your troubleshooting. You let specifications direct your troubleshooting. Right? So you're looking for two key things in any customer problem description. And I say description as contrasted with problem statement, which is what you form and you keep in your head. The customer's description is going to have all kinds of gobbledygook in it. From this gobbledygook, you're going to pick out two key things. What is the appliance doing that it should not be doing? What is the appliance not doing that it should be doing? From that, you're going to formulate your problem statement. It's going to be a very short sentence, a tight, concise statement. That's going to form your internal mission statement for that service call. It will keep you from jumping down rabbit holes and keep you from the customer, well, then I checked this and it seemed okay. I felt air at some point. You don't care about any of that. You're going to get your own data anyway. Okay, so you want to know what the customer observes, not what they think, because you're the technician. If they could figure it out, they wouldn't need to call you. Okay, you're the guy with the skills that you're bringing game on. So you just want to know what their observations are, because that's going to tell you what your problem statement should be. Now, sometimes a problem description that you'll get from a customer may contain what sounds like multiple problems. In this case, pick the most obvious problem and make that your problem statement. Rule of thumb is, well, we'll get to that, and you're just going to work that problem, right? So pick the most obvious problem and work that problem. And there's a couple of rules of thumb when you're doing this. One, you fix the most obvious problem first. You've got to do that anyway. And there's usually only one real problem on any given service call. That underlying real problem, these are rules of thumb, that underlying real problem can cause multiple symptoms, making it appear that there are several simultaneous problems. If you fix the real problem, which is usually the obvious one, you'll usually solve all the other symptoms. Because again, there's usually only one actual malfunction on any given service call. Yes, there are exceptions. But as a general rule, in my experience, there's generally only one thing that's broken at a time that can be causing all kinds of other screwy things. So you're going to formulate your problem statement from that obvious problem, and it's going to keep you focused in fixing that real problem. And you're going to use that problem statement to identify your load of interest. Your load of interest is the thing that's not doing its thing. We'll talk more about that in just a second. This is why you've got to have a clear and accurate problem statement for successful troubleshooting, because otherwise you're going to be jumping down rabbit holes, spinning around in circles, and not knowing what to do, not even knowing how to start. Okay. So a couple of exercises on that. Customer description to problem statement. Again, real customer descriptions. The dispenser water fill is dispensing too much water. This refrigerator should allow you to choose how much water to dispense. The dispenser control panel will not allow any changes. What is my problem statement that I'm going to use as a technician to direct my troubleshooting? Right? This is typical customer gobbledygook that you get, but you need to pinpoint on what is the actual malfunction. What is it doing that it should not be doing? What is it not doing that it should be doing? So in this case, a good problem statement would be dispenser UI not accepting inputs. So that tells you the dispenser UI board, the user interface board, becomes your load of interest. It's the thing that ain't doing its thing. Okay, that one should be pretty straightforward. Let's look at another one. Another customer description. Fresh food compartment is warming up. Freezer compartment's fine. Customer hears compressor running up top and feels airflow from the grill. What's my problem statement? To me as a technician, do I care what the husband does? No, I'm not interested in that. I want to know what is she actually observing as a problem, right? So the problem statement is fresh food compartment warm. I don't care what the husband hears or what he felt. I'm going to get my own data on that stuff anyway. I just want to know what are they seeing as a malfunction. That directs me and keeps me focused like a laser on the actual problem. Here, you see the customer is giving opinions. There's like an opinion on fine. Freezer compartment is fine. What does that mean? Well, I don't know, and most customers don't either. How many customers' homes do you go into where they actually have thermometers in both compartments and they know what those target temperatures should be? So what I'm pointing out here to you is that your customer, in the problem description from the customer, is going to contain a mix of observations, opinions, guesses, feelings. You're only interested in their observations. Now, obviously, you're not going to say this to the look, ma'am, I'm not interested in your guesses and feelings. Step out of the way. You're not going to do that. This is internal talk now, and we're talking as techs. All right, so once you have your problem statement, you're going to war game that problem statement. Again, this is before you even walk in the house. You're going to war game that problem statement on the schematic in order to identify your load of interest. In other words, that's the load associated with the problem statement. The load of interest is the thing that ain't doing its thing. Okay? A load is just something that loads are all about watts. It's the thing that consumes watts and does work in the physical world. It heats something, it moves something, water, refrigerant vapor, whatever, but it does something physical and real. The objective here is you want to walk into the customer's home with a troubleshooting game plan in mind, but at the same time, you're going to be open to problem conditions that you find that the customer didn't report because it wasn't even on their radar. And we'll look at an example of that here in just a bit. This process is called pre-diagnosis. Everything up to walking into the home is called pre-diagnosis. That's why I say the service call starts before the service call. And again, the whole objective is, this is part of your system, that you're going to walk into the home with a game plan already in mind. You've already got a troubleshooting strategy. You've already reviewed the technical information, and it's going to be bit, bat, boom. Get her done. Get it fixed. No need to call tech line. You've already done that beforehand, or you've posted a question on the Chat USA or at Appliantology, wherever. You've already gotten some intel beforehand if you need to. All right, let's look at let's go to this one here. Dishwasher won't drain. This is a Whirlpool-built global wash system platform dishwasher. Dishwasher won't drain. What's the load of interest? Hope you're all saying drain pump, right? Now, do we need to lay on the floor like a monkey and remove the kick panel and fumble around with our meter and try to back probe the drain pump and see if it's getting power or voltage, actually, more precisely? Personally, I hate laying on floors, and if I can avoid that, I will. I mean, I'll do it for part replacement, whatever. I mean, there's times you have to do it, but for troubleshooting, I would rather troubleshoot right from the control board because I can not only test the drain pump, I can test everything else in that machine as well, right from the control board. It's convenient. I can do it standing or kneeling on knee pads. So we can do all of our troubleshooting right from the control board, working upright like a skilled human technician. So in this case of the drain pump, what would we measure? Well, I've got a cut sheet down here, line diagram for just the drain pump, drain motor right here. And they're telling me explicit specifications. They're telling me 120 volts, blow that up a little bit. It's got a power supply of 120 volts. They're telling me the resistance of the windings, and they're giving me the wattage of that motor. All of those are explicit specifications. Okay, not a fan of resistance, but if they give it to you, it might be a good idea to use it. It's something to check anyway. In this case, you'd also want to check from the drain pump winding from either one of these connection points at the main control board to chassis ground and see if you've got some sort of path that's developed between the drain pump motor windings and ground. Okay, note there's a triac here in neutral. What does that mean about this drain pump? Right, anytime that door is closed and this K1 pilot relay is closed, that means I've got line standing on one side of that, well, actually all the way through on that drain pump. I don't have a complete circuit if that triac is open. The triac should not be closed unless I've activated a cycle. So what if I wanted to check amps on this drain pump, the preferred test for any skilled tech? Can I do that? They didn't give me amps. Well, yes, they actually did. They gave me watts, and they gave me a power supply. So I use P equals I times E again, like we did before, and I can calculate what the amps should be. So in this case, another case of amps being an implicit specification. So what would my expected amp reading be? Right, so again, I is equal to E over R is 120 VAC over 16 ohms. Hope some of you are seeing my error already. It's a deliberate error, and I'm going to use this as to explain something to you. 7.5 amps. So, I mean, is that reasonable? A drain pump is going to sit there and draw 7.5 amps while it's running? That's like the startup current on a compressor. Is that reasonable? A drain pump is going to be drawing 7.5 amps while it's running. A little dinky drain pump motor. No, it's not reasonable. What went wrong? What did I do wrong here? The problem is that I can't calculate motor amps from winding resistance because motors are inductive devices with large inductive reactance plus its normal resistance. Your meter only measures normal resistance. It does not measure inductive reactance. Inductive reactance is an opposition to electrons that is developed in like a motor winding when there's actual voltage applied, alternating current applied. Right, so you're not going to see that normally with your meter. Your meter's just using a dinky little 9-volt battery, and it's just measuring normal resistance. It's not measuring reactance, which is the other larger component of opposition to current flow in the case of a motor. So how then do we calculate amp draw? Again, you use watts, especially when you're dealing with motors. Motors are called non-ohmic. Light bulbs are non-ohmic. So you would use watts. And so you would say instead, P is equal to I times E, like we did before. Therefore, I is equal to P over E. So now I'm going to plug in the watts that they gave me over 120 volts. Now I get 0.83 amps. That's supposed to be amps, or 830 milliamps. Much more reasonable. That's what I would expect a drain pump motor to normally be drawing in operation. And then I'm going to take my amp clamp. I'm going to energize the drain pump motor in self-test mode, and I'm going to take my amp clamp and put it around here. And I'm going to measure the amp draw on that drain pump motor. Much better test than just measuring the resistance of the windings. I mean, now you're testing it as though it's really running, because it is really running, and you're testing it under run conditions. So if you measure much higher amps than what I should be getting, what if I measure like 2 amps? What does that tell me about the winding resistance? means the winding resistance must be way low out of spec. Must be much lower than that. Because you got to have lower resistance in order for more electrons to be forced through that load by the voltage difference developed across that load. Hope that makes sense. So let's look at an example here. Another example. Dryer runs forever on auto dry. What is my load of interest? Let's blow that up a little bit. Dryer's running forever on auto dry. What's my load of interest? Again, remember, a load is the thing that actually does something in the physical world, and it's all about watts. Motors, heating elements, lights. So I hope you're all saying that the load of interest is the timer motor. Not just timer. A mechanical timer has two parts, the contacts, and if you want to include the cam that moves the contacts, these are the various different contacts around here that you see. Up here. Those are timer contacts. Those are just switches. And the timer chart tells you which switches are open or closed in the cycle. But the actual part of the timer, again, you got to narrow in, is the timer motor itself. Right, so then all I would do at this point is use the timer chart right here to determine which switches should be closed during auto dry. And then I'm gonna draw that in, and I'm going to analyze the power supply circuit for this timer motor. And then I'm going to see which switch is open. Do I have something grounded? Do I have something that's stuck closed? Maybe one of the other control switches. Maybe this timer motor is being shunted by something stuck closed, one of these bimetals. That does happen. That's another way the timer motor power supply can be bypassed. All right, so once you've got your TechLid on your iPad, you've war-gamed it and all that, and as a result of your war-gaming, again, you're interacting with that system, those steps 2, 3, and 4, you're going to bookmark your disassembly procedures in the service manual. So for computer-controlled appliances, you can do most of your testing from the board with minimal disassembly, as we've talked about. And that applies to appliances with mechanical timers, too. Even the one we were just looking at, that GE dryer. I can do my troubleshooting right from the timer. I've got the schematic. Why do I need to tear it apart? I'm going to bookmark pages in that service manual that show how to access the board or the board pinouts, where I'll do most of my testing. And I'll bookmark pages showing access to the load of interest in case I've got it with me and I can go ahead and replace it. Okay, disassembly is actually the lowest skill part of what we do. It's maybe a shocking statement. It shouldn't be. But it is. It's the lowest skill part of what we do. It's still a skilled part of what we do, but it's the lowest skill part of what we do. But the thing is, it's the one that the customer sees. So you don't want to be bumbling around and looking like a boob when you're trying to disassemble the appliance to get to it, to get your test points, to get to your load of interest if you're going to be doing the replacement. So you want to have those already bookmarked in the service manual. This will also help you avoid damage and minimize your liability. All right, a few more slides left, and then we'll be done. Finally, you want to be observant. This is the last step in the system. Be observant and responsive to unexpected findings not reported by the customer. This can change your troubleshooting on a dime. Customer may not have reported something that turns out to be very diagnostically significant and could really alter your problem statement. But you'll still be ahead of the game because your pre-diagnosis that you've done will speed you up. It's going to speed you up because you're going to be able to adapt to it because you're already familiar with the technical literature and some of the basics of the operation of the machine. Let's get an example of that. Curveball example. Customer reports that the freezer is cold. Most customers don't know what cold is in a freezer, right? What's the target temperature in a freezer? Should be 0, right? But for a lot of customers, if that freezer's at 10 or 15, and they won't even know because they don't have a thermometer, 10 or 15, even 20 degrees, they'll think it's fine. So anyway, or they'll think it's cold, whatever. But the fresh food compartment is warm. Now that's probably a real problem. When a compartment is too warm, that's probably real, even if there's not a number on it, and that would become my problem statement. So you start wargaming a warm, fresh food compartment. You look at evaporator fans, how those work, the dampers, the gaskets, defrost system. When you arrive, though, you shoot both compartments, as you should. Anytime I go on a refrigerator service call, even if I'm there just to replace a handle or whatever, I shoot both compartments with my IR gun. The reason is there may be a problem going on with that refrigerator that was completely off the customer's radar. They weren't even aware of. So I shoot those compartments and I find the freezer at 15 degrees and the fresh food compartment at 45. Sure enough, fresh food compartment is warm, just like the customer said, but they thought the freezer was cold. I see a freezer at 15. I go, Houston, we have a situation. Does this change your troubleshooting strategy? Yeah, sure does. Because now instead of just dealing with, evaporator fans, dampers, and all this stuff, now I have to half split the problem. Do I have a sealed system problem? I should be asking myself that. Do I have a sealed system problem, or is it everything else outside of the tubing and the compressor? Right? So do I need to disassemble the freezer to look at the frost pattern? That's what everybody likes to go to. That's the go-to. Oh, got to take all the food out of the freezer and disassemble it and look at that frost pattern. All right, well, you guys can do that if you want, but again, I'm presenting to you my system, and I'll give you a little trick here as a bonus. You don't need to do that. You can look at the condenser temperature split, assuming that your condenser is clean, your condenser fan's running, yada, yada, right? We know the drill. You can look at the condenser temperature split, and that is the temperature of the saturated zone of the condenser minus the ambient temperature. That's called the split. And that's by design 30 degrees. Anything above 20 is probably okay. Doesn't mean that necessarily the sealed system is quote good, but it's a screening test. So if I see something below 20, for example, I have a problem. It's like an Ohm's test in that case. If Ohm's test is bad, in other words, open, something like that, or shorted when it shouldn't be, then yeah, I found a problem. But if the ohms are in spec, I haven't necessarily found a problem. Similarly with the condenser split trick. If my condenser split is too low, or it would actually be too high, less than 20 degrees difference between condenser saturated zone, that's the middle of the condenser, and ambient temperature. Saturated zone in a condenser, your first couple of rungs are superheated. Your middle, most of your condenser in the middle is saturation, and your last rung or two is subcooled. So if I've got a condenser split that's less than 20 degrees, we got a problem. And to understand why this works, I refer you to either the refrigeration course at Master Samurai Tech or the Sealed System Thermodynamics webinar series at Appliantology. So just to review and wrap up with the system that I roll with, that I've developed over a number of years, validate the model number, get that technical literature with your validated model number, put it on your tablet, formulate your problem statement from the gobbledygooky customer description, wargame that problem statement on the schematic to identify your load of interest. That's all your pre-diagnosis. You're going to bookmark the relevant sections in your technical literature that's on your tablet so you can access it quickly while you're on the job. And then just be prepared to revise your problem statement based on your observations at the call. Okay, so we went a little bit over time, but we were a little bit late getting started, so apologize for taking up more of your time. Tried to keep it to an hour. So thank you all for coming out. And Sarah, I don't know if you're going to open it up for questions or what the procedure is at this point, but I'll turn it back to you.
Thank you, everybody, and thank you, Scott, for attending our webinar today. If you have any questions, send us an email at administration@unitedservicers.com, and we can send you the link to rewatch. Thanks.